Yes. Okay, so welcome back. Welcome to the second session of the course Optimization for Data Science. So as I mentioned, what I want to do this second session is to cover the gradient method, which is the simplest possible method for optimization that probably every one of you has heard of. So what I would like to do, this will be a way for me to use some of the concepts that we introduced in the section this morning, like strong convexity and smoothness and so on, so to apply them in the analysis of the gradient method. So what I will do is that I will go through the analysis of the gradient method. We'll do some proofs. We will show what are the weaknesses of the gradient method. And I will discuss, give you some observations about the gradient method. And then tomorrow, we will try to see how to fix those, or what are other alternatives other than the gradient method, some more advanced methods that converge faster than the gradient method and then have better properties. So, I think today's, this afternoon session maybe will be a bit shorter. Maybe it will be just 1 hour instead of 1 hour and a half. So we'll see how it goes. Okay, so let's see. So the question, so this is the simplest question we want to look at. So it's an unconstrained problem, unconstrained optimization problem. I fix a function f, and I want to minimize this function. Again, I'm going to look at convex functions mostly in this course so that we can give guarantees, so that we can prove things about the algorithm. So, so the question, I want to minimize f of x. As we've seen, for convex functions, any local minimum is a global minimum, so we can hope to reach the global minimum of this optimization problem. So we want to reach f star. Okay, so the gradient method is very simple. It's summarized in this one line that's highlighted in blue that you see. So you start from some iterate x0, and then you look at the gradient of the function f. Okay, so that is a vector in Rn. Okay, and then you move along the negative gradient of the function. So if you have a point xk, okay, if the gradient of your function is like this, gradient of f at xk, okay, so you move in the opposite direction, okay, by a certain magnitude tk. Tk we call the step size, okay, and your new point, this is going to be xk plus 1. Okay, I have, so the gradient method is not completely defined in the sense that I did not say exactly how the step size is chosen. So in order to completely specify an algorithm, you need to say how the step size is going to be chosen at each step. And we are going to talk about this. There are various ways to do this. If you know some parameters of the function, like the smoothness parameter or the strong convexity parameter, then you can choose tk according to this. Or if you do not have any information about your function, any prior information, you can do an adaptive line search, what we call a line search, and I will explain this at the end of today's lecture. So why the gradient method? So the gradient method, why do we choose the gradient as the direction? This is probably just this is just based on the first order Taylor expansion. So so if you remember, let me write here at the top. So if you remember, I have f of x plus h is approximately equal to f of x plus gradient of f of x transpose h. Okay, let me just repeat that. Okay, so so now if we are interested in minimizing f. So so starting from x, I want to know what is the direction that will minimize this right-hand side. Okay, if you fix the norm of h to be 1, okay, this is the smallest possible when h is the negative of the gradient. Okay, so So it is really based on a first order Taylor expansion of f around x and choosing the direction that is where the function changes the most in the negative direction. Okay. So this is the gradient method. As you can see, the iterations are very cheap. You just need to add vectors to each other. So once, yes, so I will explain how to choose the step size as we go. Okay, now I said that the algorithm is not completely specified, so I'll explain how to choose the step size. Yeah, so as I said, the iterations are very cheap. So you just need to update the vector xk by adding to it another vector, the gradient. And note that the only thing that we need about the function is just what we call a black box access to the gradient. So you just need a way to compute the gradient of f at a given point. Okay, this is what we call the oracle model in optimization, in the sense that you don't need to have a full description of your function, like a formula or anything. You just need that someone gives you access to the gradient, so that you can call a function at a certain at x. You give it input x, and it will return to you the gradient of f. Okay, so this is what we call a first order method in optimization, because it only relies on access to the gradient of f. Later on, we will look at other methods that are based on second order information. So also a black box access to the Hessian of f, the second derivatives of f. Okay, so okay, so this is the gradient method. So so now I can let me immediately give you the result about I mean, one result that one can prove about this gradient method is that if your function f is not only convex but is actually strongly convex with a parameter m here, okay, and if it is L smooth as well, okay, so we assume that, remember, this means that the Hessian of f, assuming that f is twice differentiable, that the Hessian of f has eigenvalues between little m and big L, then if you choose this constant step size, okay, so if you choose for all k, tk is equal to 2 divided by m plus L, okay, then the method actually converges, and converges at a linear rate. Okay, so so this is something that you can prove here, is that the norm of xk minus x star, so how far you are from the optimal point x star, you can show that this is less than the following quantity raised to the power k times norm of x0 minus x star. So norm of x0 minus x star is your initial, this is initial distance to optimum. Okay, so this is initial distance to the optimal point. Okay, and this algorithm tells you that at each step of the algorithm, you are multiplying, you are essentially dividing, if you want, your distance to the optimal point by a certain number greater than 1. Okay, and what is the rate of convergence? It is this. This is the rate of convergence. This c minus 1 divided by c plus 1. Okay, so c minus 1 divided by c plus 1. That's a number, okay, that you can compute from the parameters of your function, and c here is the ratio of L divided by m. Okay, so that's sometimes, very often, in fact, called the condition number of the function. Okay, and you note that c minus 1 divided by c plus 1, that is a number strictly less than 1. Okay, so at each step of the algorithm, what we're saying here is that the distance is being multiplied, the distance to x star is being multiplied by a certain number strictly less than 1. Okay, so this means that yeah, so this means that eventually you will reach your distance to x star will converge to 0 at a linear, or if you want to call it also a geometric rate. And if you work out, so if you work, no, c cannot be 0. If you work out the c is greater than or equal than 1, because it's L divided by m, and we've seen that L is always bigger than m. So if you want to reach an accuracy epsilon, so if you want to be epsilon away just from x star, then by just working out that c minus 1 divided by c plus 1 to the k is equal to epsilon, okay, then this will tell you roughly that k has to be roughly equal to c log 1 over epsilon. Okay, so this means that if you want to be epsilon away from the optimal point, this is the number of iterations you have to do. So it's the condition number times log of 1 over epsilon. So let's plug in some values to get an idea of this. So if you want to reach epsilon, let's say 10 to the minus 4, okay, so 1 over epsilon 10 to the 4, you take the log of this, that's roughly 4, obviously, so it depends on the base. So that's roughly 4. And then you have to multiply this by the condition number, okay? Yes, so this is kind of the result that one can prove about the convergence of the gradient method for strongly convex function. Okay, so this is really important. This is for strongly convex functions. Okay, we will see later on a result for the convergence for non-strongly convex functions, and we'll see that the convergence is much slower typically. Okay. So okay, so now I hope the statement of this result, this convergence result, is clear. So it tells you that if you choose a certain constant step size, then your gradient method will converge to the optimal point with a certain rate, okay, which is given by c minus 1 divided by c plus 1. Okay, so let's actually now prove this result. Okay, so so remember that. So let's write first the iteration rule from the gradient method. So that's oops. Okay, so that's xk plus 1 is equal to xk minus tk times the gradient of f at xk. Okay, now I'm interested in the distance between xk and x star. So let me write, this tells me that xk plus 1 minus x star is equal to xk minus x star, okay, minus tk times the gradient of f at xk. Okay, so this is the distance from x star is the same as the distance xk minus x star minus this term involved in gradient. So now what I'm going to do is I'm going to use a formula for the gradient of f at xk. So I claim that the following is true, that the gradient of f at xk, okay, so this is equal to the gradient of f at x star plus the integral from 0 to 1, okay, of the Hessian of f, okay, at x star plus, okay, let me not use t, plus some alpha times xk minus x star times xk minus x star times d alpha. Okay, so where is this formula coming from? So this formula is nothing but the fundamental theorem of calculus applied to the function, the gradient function. So let me explain this more in detail. So, okay, so you call phi, let's call it phi of alpha. Okay, this is the gradient of f at x star plus alpha times xk minus x star. Okay, so the formula at the top is just the fact that phi of 1 is equal to phi of 0 plus the integral from 0 to 1 of phi prime of alpha d alpha. Okay, and phi prime of alpha, if you use the chain rule, this is equal to the Hessian of f at x star plus alpha times xk minus x star, okay, times xk minus x star. Okay, this is by the chain rule. Okay. So now what is nice about the formula at the top in blue is that now this guy, because I know that x star is my optimum, so so this guy here that you see, this guy is equal to 0. Okay, so this guy is equal to 0. So this is telling me really, if I jump here, that this is equal to So a certain matrix M times xk minus x star, okay, where M is equal to the integral from 0 to 1 of the Hessian of f at x star plus alpha times xk minus x star d alpha. Okay, so you can see that M is an integral of matrices, but that's fine. I mean, it's the integral of the individual entries if you want. So M is the integral of these Hessian matrices on the line between x star and xk. Okay, so now let me use, this is the gradient of f at xk. So the gradient of f at xk is m times xk minus x star. Now I can plug this in this formula. Okay, so so let's do this. So I have xk plus 1 is equal to, xk plus 1 minus x star is equal to xk minus x star minus tk times m xk minus x star. Okay, and so this is really equal to identity minus tk m times xk minus x star. Okay. Okay, so my k's are not very good, but this is really what we get. So we get a linear relationship that xk plus 1 minus x star is a certain matrix applied to xk minus x star. Now, what this really means is if I take, now I'm interested in the norms and the distances from xk to x star. So this implies, okay, that the norm of xk plus 1 minus x star, the two norm, this is less than what I will call a rho of I minus tkm times the norm of xk minus x star. Okay, where? So rho of I minus tkm, okay, is the largest eigenvalue of I minus tkm in absolute value. Okay, if you want, it is the operator norm, if you want, of identity minus tkm. Okay, but in more concrete terms, you look at the largest eigenvalue of identity minus tkm. You take the largest one in absolute value, and this is the rho of I minus tkm. Okay, but let's actually go back to what is M. So M was this matrix. Okay, so M is an average of Hessians. Okay, so, and we know that each Hessian has an eigenvalue. All its eigenvalues are between L and M. Okay, and so this means that M, the matrix big M itself, has all its eigenvalues between little m and L. Okay, so okay, so since now let me continue here in red. So since okay, the Hessian of f is always, since the Hessian of f is always between L identity and M identity. So remember, this is what I mentioned last time. This means that all the eigenvalues are between little m and big L. Okay, this means that M is between L identity and M identity. Okay. Again, this is the order, meaning again that the eigenvalues are all between little m and big L. Okay. So, but this in turn, this implies that eigenvalues of I minus tkm are all in the interval 1 minus tkl and 1 minus tkm. Sorry. Okay, they are all in this interval 1 minus tkl and 1 minus tkm, because when you add identity to a certain matrix, you just shift the eigenvalues by 1. Okay, So now, okay, so now it's a matter of understanding. So this means this in turn, this implies that rho of I minus TKM is the max of the two absolute values here, is the max of 1 minus TKL and 1 minus TKM. Okay? I hope that is clear. So remember, let's recap what we've done. Okay, we were able to write xk plus 1 minus x star as a linear operator applied to xk minus x star. And now what we want to do is to analyze the eigenvalues of this operator, identity minus tkm. So using properties of the Hessian, using the assumptions that we have on the function, we were able to say that the eigenvalues of this operator are all between 1 minus tkl and 1 minus tkm. Okay, and so the largest eigenvalue in absolute value is really the max of these two absolute values here. Okay, so now let's plug in. Remember, so now recall. So now the value we mentioned that we're going to use the value tk is equal to 2 divided by m plus big L. Okay, so actually for this choice, what we have is 1 minus tkn, so that is equal to 1 minus 2L divided by m plus L. Okay, and what you get in here is you get, so if I take absolute values, you will get exactly L minus m divided by L plus m. Okay, which is exactly equal to this c minus 1 divided by c plus 1. Okay, and as well 1 minus tkm. If you do the computation, you will get the same. This is also equal to c minus 1 divided by c plus 1. Okay, so for this choice of tk, this means that rho of identity minus tkm is really equal to c minus 1 divided by c plus 1. And so this implies then that the norm of xk plus 1 minus x star, the 2 norm, is less than c minus 1 divided by c plus 1 times the norm of xk minus x star. Okay, and so this is exactly what we wanted to prove. So obviously then this means that the norm of xk minus x star, by iterating this, that the norm of xk minus x star is less than c minus 1 divided by c plus 1 to the power k times the norm of x0 minus x star. Okay, if you want to go all the way to 0. Okay, so so really maybe if I can say what is the main part of the proof is really to write the gradient of f at xk in this form. So it's really this this formula that you see here, this one. This was really the heart of the proof, and then it was just a matter of using the properties that we know about the Hessian to infer things about the eigenvalues of m and about identity minus t times m. Okay, so and I would say this is linear algebra mostly. So okay, so I hope that is that was clear. I mean, even if maybe some of the steps you you could not follow, I hope that the main idea was kind of clear. So okay, so we have shown then that the method converges linearly. So the norm of xk minus x star is less than c minus 1 divided by c plus 1 to the power k. So okay, so I've implemented the method on a simple example on this squared squared loss. So the linear regression problem that we've seen in the this morning. So remember here that the gradient of f is equal to I mentioned last time A transpose x minus b, and so the Hessian of f is just A transpose A. In fact, it's constant. It doesn't depend on x. And so in this case, little m is the smallest eigenvalue of A transpose A. Okay, and big L is the largest eigenvalue of A transpose A. Okay, so here, what you can see here, so I've ran the gradient method for 100 iterations on this function. And what I have plotted, you see this is a log scale here. I have plotted f of xk minus f star. I could have plotted as well the norm of xk minus x star. It would, the plot would be very similar. Okay, but I have plotted here the function values, f of xk minus f star, versus the iterations. And what you have seen that in the log scale, what you have is a line, essentially a straight line, and this is indicative of a linear convergence rate. Okay, you can see this is really linear convergence rate. Okay. And the slope is directly related to the rate of convergence. I mean, this c minus 1 divided by c plus 1. Okay. So we can verify essentially the what we have just proven. We can verify it experimentally by running the gradient method on this example. Okay, so this was this is the behavior of the gradient method on strongly convex functions. So now, what happens if I apply my function to my gradient method to a function that is not strongly convex? Okay, and this is what I want to state next. This is an important result in optimization that any research, I mean, anyone doing some research in optimization and algorithms should know. I mean, so this is, I mean, if your function f is convex and L smooth, so I don't assume anything about strong convexity. I just assume that it's L smooth, meaning that all its the eigenvalues of the Hessian are at most L. Then with a constant step size, which is 1 over L this time, so we don't have the mu, so it's just 1 over L. Then you can show that the function values f of xk minus f star is less than L divided by 2k times the norm of x0 minus x star squared. Okay, so again, you can see that this will converge to 0 as k go to infinity. Okay, but the convergence is much, much slower. Okay, this is what we call a sublinear convergence rate. Okay, so well, for example, if you want to reach f of xk minus f star is equal to epsilon, okay, what you need is L over epsilon iterations. If you just plug in, if you just set this to be equal to epsilon, okay, this will tell you that roughly k has to be roughly L over epsilon. If we kind of skip the norm of x0 minus x star squared term. And this is much, much larger than log 1 over epsilon. Okay, so this is a much worse convergence rate than the linear convergence rate we saw before. I've put some values just to kind of make this concrete, and so we can see very easily. Let's say you want to reach an accuracy of 10 to the minus 4. Okay, what this is telling you is that if your function is not strongly convex, you'll have to do in the order of 10,000 iterations. Okay, whereas in the gradient method, you just have to do a handful of iterations. Okay, so log 1 over epsilon in this case is just 4. Obviously, there are constants I have to multiply this with and so on. So in practice, it's not 4, it's a bit more than this. But this is just telling you the scale. I mean, we're talking about different orders of magnitude. Okay, so sublinear convergence rate is typically much slower than this linear convergence rate we have. Okay, but this is what we have to pay if your function is not strongly convex. Okay, so what I would like to do now is to prove this result. And okay, so let's go to the proof. So the first step of the proof. So remember that so f is L smooth. Okay, remember L smoothness. So L smoothness really tells me that f of y is less than f of x plus the gradient of f of x transpose y minus x plus L over 2 times the norm of y minus x squared. Okay, so I have a quadratic upper bound on f. So I'm going to apply this with y is equal to xk plus 1 and x is equal to xk. So this is telling me really that f at xk plus 1 is less than f at xk plus the gradient of f at xk transpose. So xk plus 1 minus xk, xk plus 1 transpose xk, and then I have plus L over 2 times the norm of xk plus 1 minus xk squared. Okay. Let me do this. Yes. Okay, so but now we know, so I know that I know that xk plus 1 minus xk is equal to minus tk gradient of f at xk. In fact, I know that tk is 1 over L, so let me just write is minus 1 over L times gradient of f at xk. So what this allows me to get is that this is equal to f of xk, so minus 1 over L times the norm of gradient of f at xk squared. Okay, and then I'm going to plug this in here as well. So I will get plus 1 over 2L norm of gradient of f at xk squared. Okay, and then if you combine everything together, you'll get f of xk minus 1 over 2L norm of gradient of f at xk squared. Okay, so what I have shown is that f of xk plus 1 is less than this. Okay, so already we can see a certain consequence here is that, I mean, this is obviously this is strictly less than f of xk. Okay, so this means that this is gradient is a descent method. So descent method meaning that the values of the function will decrease. You have there exists some optimization algorithms where the value at xk plus 1 can increase. Obviously, in the overall, if it converges, it has to decrease, but it is possible. Some algorithms have that the f of xk plus 1 can be bigger than f of xk. In this case, for the gradient method, this is not possible. So f of xk plus 1 is always strictly less than f of xk for this choice of step size. Okay, so so we'll have to remember this. So this is important. So now I'm interested. Let's go back to the proof. So I'm interested in bounding the difference f of xk minus f star. Okay, so what I can do, I can just write f at xk plus 1 minus f star is less than f at xk minus f star. Okay, and then what I will do here, I will also yes, so I will do this. So I will write minus L over 2 times the norm of xk plus 1 minus xk squared. Okay, so compared to this, so what I have done is I have changed the gradient of f at xk. I've changed it by L times xk plus 1 minus xk. Okay, so because this will be useful, I will need this expression later on. So okay, so now let's use another fact of convexity. So okay, so by convexity of f I know that f at x star is bigger than f at xk, okay, plus the gradient of f at xk transpose x star minus xk. Oops, sorry. Let me make some more space. By convexity of f, okay, I know that f at xk, f at x star, okay, is bigger than f at xk plus the gradient of f at xk. Okay, remember, this is what you get from the fact that the Taylor expansion, that the first order Taylor approximation of f at xk is a lower bound to the function everywhere, in particular at x star. Okay, and so this, in particular, this implies, if I rewrite this, this implies that f at xk minus f star is less than the gradient of f at xk transpose xk minus x star. Okay, so now what I'm going to do is I'm going to plug this expression, this inequality, I'm going to plug it in here. Okay, and then okay, so let's continue in the next page. So so remember, let's just recall what we've proved. So we've proved that f at xk plus 1 minus f star is less than f at xk minus f star minus L over 2 norm of xk plus 1 minus xk squared. And what I know is that this is less than the gradient of f at xk transpose xk minus x star minus L over 2. Okay. Okay, and then now what I'm going to do is I'm going to say that this is equal to, so this is equal to minus L times xk plus 1 minus xk transpose xk minus x star minus L over 2. Okay, so you should see why this is true. This is because, remember, xk plus 1 minus xk is equal to minus 1 over L times the gradient of f at xk. Okay, this is the iteration rule. And I've just replaced, I've just done the replacement in here. Okay, and then now I'm almost done, so I can just rearrange this, this expression. Okay, I'm going to write that this is equal to minus L, so minus L over 2 times the norm of xk plus 1 minus x star minus xk, sorry, squared. And then I will have minus xk plus 1 minus xk transpose minus 2 transpose x star minus xk. Okay, so the signs should be okay. Okay, and then now I'm just going to recognize a certain, I'm going to simplify this expression. So note that this expression is of the form norm of a squared minus 2 times a transpose b, okay, where a is equal to xk plus 1 minus xk, and b is equal to x star minus xk. Okay, let's see. So I think this should be, I'm looking at my notes, I think this should be, let's see, so this I think should be x, it should be xk minus x star. Okay, sorry for the, this is xk minus x star. And so, okay, so then if you use the fact that norm of a squared minus 2 a transpose b is equal to the norm of a minus b squared minus the norm of b squared. Okay, so what you will get is that this is equal to minus L over 2 times the norm of xk plus 1 minus x star squared minus the norm. Okay. I actually think, let's see, I think I was actually correct. The sign was correct. Let's see. So this xk plus 1. B should be x star minus xk. Actually, I think I was correct. Sorry. So this should be so this should be x star minus xk. Check. And x star minus xk. Okay. So at the end, this is what we get. Okay. So so please bear with me. I mean, the proof is slightly more complicated than the other case. I mean, the strongly convex case. So we have that f of xk plus 1 minus f star is less than minus L over 2 times this difference. So now what is nice about this difference is that I can sum these inequalities, and then these things will cancel out each other. I mean, this is usually how such proofs are conducted. So now if I sum now if I sum this inequality, so I will get the sum from k equals 1 to t minus 1 of f of xk plus 1 minus f star. This is less than minus L over 2, and then I will just have the first term and the last term. Okay, so this I will just get minus norm of xt minus x star squared minus the norm of x0 minus x star squared. Okay, because everything else will cancel. Okay, and then I can actually upper bound this by L over 2 times the norm of x0 minus x star squared. And okay, so now I'm kind of almost finished. Now we just have to realize that this guy. So since the gap, I mean f of xk plus 1 minus f star, since this gap is is actually decreasing, okay, so this guy is actually, I can lower bound it. So so this is okay, what do I write? So okay, let me just say on the other hand, okay, the sum of f at xk plus 1 minus f star, okay, equal 0 to t minus 1. Okay, so this is bigger than t times f at xt minus f star. Okay, I can, because I know that the last term is the smallest one. So this whole summation is bigger than t times the last term, because this is the best, this is the closest possible to the solution. Okay, so at the end, what this tells me is that f at xt minus f star is less than L divided by 2t times the norm of x0 minus x star squared. Okay, and this is so this is really the this is what we really wanted to prove. Okay. So it shows that the tth iterate f at xt minus f star is less than L divided by 2t of this norm of x0 minus x star squared. So the proof really, I mean, if we go back to the proof really involved two main inequalities. The first was the usage of the L smoothness. Okay, this inequality. This is the first place where we use L smoothness really, and the only other place, the fact where did we use actually convexity is really in here. Okay. It is to bound f of xk minus f star by the lower I mean the first order Taylor expansion at xk. So these are really the two main inequalities that we use about f, and then the rest kind of is a matter of combining these inequalities together in a nice way. Okay, I don't say it's easy, but really the key part are these two inequalities about F. Okay, this proof that I presented is a more or less standard proof that you will find in many references on convex optimization. Most modern treatments of the gradient method will involve this proof exactly. So, because this proof is also used, a very similar proof can be used to bound the convergence of something called the proximal point method that we may discuss in 2 days or so. Okay. So, okay, so this was the proof of this method. So now let's look at an example. So I've applied it to a function that is not strongly convex, to a problem in logistic regression, where the function is, remember this function that we looked at in the morning. So f at t is the log of 1 plus exponential t. Okay, so this is related to the logistic loss. So when you want to do regression, but you have your response is say +1 or -1, so use such a loss. And so in logistic regression, you want to minimize a certain summation of such terms. And so so this, I mean, we've seen that this function f is not strongly convex because it approaches to it approaches something linear at infinity. And so if you run the gradient method on this on such a function, you will see that we don't see we don't see this linear convergence rate as we've seen in the least squares problem that I've shown before. So we don't see a line, rather we're seeing kind of a much slower convergence. Okay, so I've ran it here for 100 iterations, and we see that after 100 iterations, in fact, the gap is still quite big. Okay, f of xk minus f star is in the order of 1. So okay, so the gradient method is quite slow for this function here. Okay, so so let's, I mean, now I would like to, now we've proven this result, I want to kind of give you, tell you some observations about the gradient method, what its main drawbacks, and then this will allow us, this will motivate somehow the discussion tomorrow about how to look for methods that are better than the gradient method. Okay, so now this is, I would like to talk about the sensitivity of the gradient method to scaling. Okay, so so now this figure that you see here, which I borrowed from slides of Lee van Vandenberg from UCLA, is the gradient method applied to a quadratic function, a convex quadratic function on the plane. So in R2, so you just have two variables. Okay, the minimum of the function is at the origin, the center of the figure that you see here. And this is the point that you see in here. This is x0. Okay, and then this is x1, and so on and so forth. Okay, so I mean, this zigzagging, you see that there is this zigzag behavior of the method. Okay, so the gradient of the method will take you down from x0, and then it will take you up and then down again, and so on and so forth. And this will all depends on gamma. Okay, you can see that as gamma gets close to 0, so if gamma is equal to 1, there is no zigzagging. If gamma is equal to 1, in this case, the level sets of the function, so these ellipses are actually just circles, and then the gradient actually points directly to the origin, to the minimum of the function. So there isn't going to be any zigzagging. So the method will actually converge very quickly. But as you let gamma go to 0, so there is going to be more and more zigzagging. And in fact, you can show that in here, the condition number, okay, so the condition number, so the condition number, in this case, is just C is equal to 1 over gamma. Okay, because the largest eigenvalue of the Hessian is 1, and the smallest eigenvalue of the Hessian is gamma. So 1 over gamma. Okay, so here he's actually choosing gamma to be bigger than 1, so it's the other way around. So the condition number is just gamma. Okay, so as gamma goes to infinity, I mean, these circles will tend to be more flatter and flatter ellipses, and so the problem will be more and more ill-conditioned. Okay, and so there is going to be more and more zigzagging behavior. So this is kind of an undesirable feature of the gradient method, because it is very sensitive to scaling. I mean, if I want to kind of make this point a bit clearer, the idea is that, let's say you want to you have a certain function, okay, by just rescaling some of the variables, by just calling, instead of x1, the variable x1, you change its scale, you divide it by 10, let's say, and the second variable you multiply by another constant, and so on. This doesn't really change the function; it just changes the kind of the scaling of my domain. The behavior of the optimization algorithm will actually change, and this is something quite undesirable, because this means that in practice, what you'll have to do is to pre-scale your problem so that the condition number is close to 1. And kind of to make this point, maybe to explain this behavior, this sensitivity to scaling in a different way, we can kind of do this simple exercise of doing a change of variables, an invertible change of variables, and running the gradient method on this new function where you did the change of variables. So let's say your original space, your original component coordinates was x. Let's say now I have an invertible matrix P, and I define new coordinates which I call y, and this is P inverse times x. So this corresponds to defining a new function f tilde of y is equal to f of py, and you apply the gradient method to f tilde. Okay, so if you apply the gradient method to f tilde, these are the iterates that you get. So yk plus 1 is equal to yk minus tk times the gradient of f tilde at yk. And so now, because the gradient, okay, the gradient of f tilde at yk, this is equal to, by using the chain rule, again, this is the p transpose gradient of f at p times yk. Okay. So really the iterates are, so this is by the chain rule. So the iterates are really yk plus 1 is yk minus tk p transpose gradient of f at pyk. So now if I multiply things by p on the left, because xk is equal to p times yk, what we get is this iterate, is this iteration rule. And then what I want is to compare this with xk plus 1 is equal to xk minus tk times the gradient of f at xk, which is what you do if you apply the gradient method directly to the function f. So you can see that unless pp transpose is equal to identity, then this is going to be a different iteration. Okay, then the iterates are going to be different in general. Okay, what this actually means geometrically is something very simple. If I go back to this slide, pp transpose is equal to identity means that the transformation that you're doing is just a rotation or a reflection. Okay, so this doesn't really change anything. Okay, the gradient method, still the gradient will always point to the origin in this case, and you will converge very fast. But pp transpose not equal to identity means that you're doing some scaling like the gamma here. Okay, so you're changing these circles into ellipses, and this will change the behavior of the gradient method. Okay, so so this is something that one has to be aware of, and this is, I mean, there is a reason why this happens, is because the gradient, the notion of the gradient mathematically depends on the inner product that you choose. Okay, so remember how we actually introduced the gradient. We introduced it as so we introduced it f at x plus h is equal to f of x plus the gradient of f at x transpose h plus a big O of h squared. Yeah, sorry. So plus a big O of the norm of h squared. So now this guy, so this vector, the gradient of f at x, is I mean, yeah, the notion of gradient depends on the fact that here I'm using the standard inner product on Rn. If I were to use a different inner product, the notion of gradient would change. And choosing a different inner product, I mean, by changing the coordinates, by doing a coordinate, a change of basis, what I am essentially doing is changing the inner product. So I should use a different choice of gradient. I mean, we will discuss a little bit this issue when I talk about the Newton's method, because Newton's method is a method that is insensitive to scaling. Okay, so let's see, what do I want to, okay, so I would like to talk now about line search. So so what we did, I mean, the previous two results, I presented the analysis with a constant step size. So assuming that you know properties of your function, mu and L, and based on this, you would choose the step size tk, and in both cases, I used the constant step size. So in practice, though, the constants L and or mu are hard to estimate or just unknown. And so what we do in this case, if they are unknown, is that we use what we call a line search. So at each step, if you are at xk and you know that you have to move in the direction gradient, but you don't know by how much you have to move, what is the magnitude, this tk, okay, is that what you is that we look for a tk such that you achieve sufficient decrease in function value compared to f of xk. Okay, and the typical criterion that we use is the one that you see highlighted in blue. So forget for now about the gray part that you see on the left, just focus on the blue part. So what you want is that f at xk minus t gradient of f at xk, which is, this is going to be your xk plus 1. You want that this is smaller than f at xk minus a certain constant alpha. You can think of alpha as just being 1/2, let's say, to fix ideas. Alpha times t times the norm of the gradient of f at xk squared. Okay, so let me try to explain where this right-hand side is coming from by just drawing a simple picture. So, okay, I hope I can draw this nicely. So remember, once we fix the direction, the gradient, I really should think about my function restricted to this one-dimensional line. Okay, so let me talk about phi of t. This is equal to f at x minus t times the gradient of f at x. Okay, so this is just a function of one dimension. Okay, so I can draw here. So I'm going to draw this. So okay, so I draw this, and then okay, so I have my function is convex, so it's going to be convex on this line. So it's going to look like this, for example. Okay, and so my function is convex, so it's always above okay, this is the linear approximation. So let's see, so this is my variable t. Now this function that you see in green here, so this is the first order Taylor approximation. So in this case, it's just phi of 0 plus t times phi prime of 0. Okay, and in this case, if you use the chain rule, that's exactly f of x. Okay, so minus t times the norm of the gradient of f at x squared. Okay, because here, if you do the chain rule, so here phi of 0, so phi of 0 is equal to f of x, and phi prime of 0 is just minus the norm of the gradient of f at x. Okay, so this is really phi of 0. So now the iterate xk plus 1 that I'm looking at, that I would like to find, is a point that achieves a sufficient decrease. So what I'm going to put here, so let me, the colors are not so nice, so let me try with red here. So now this, I'm going to consider this line. Okay, so now this line is, this is phi of 0 plus my alpha times t times phi prime of 0, where alpha is between 0 and 1. Okay, and the xk plus 1 that I'm going to look for has to have a value of f that is below the red line. Okay, so I'm looking for so xk plus 1 has to be somewhere in here. Okay, so this could be my step size tk. Okay, this is a valid step size. Okay, and this tk, this is an invalid step size. Okay, because it is above the red line, even though maybe it actually decreases. So if you compare it to f of xk, okay, if you compare it to f of xk, maybe it will be still a decrease, but it is not what I call sufficient decrease. Sufficient decrease means it has to be below this red line. Okay, and this red line is just obtained by taking the green line and tilting it a little bit by applying this alpha, which is between 0 and 1. Okay, so I hope, okay, so alpha is between 0 and 1. I hope this is clear. So backtracking line search, which is the title of this slide, the way this is typically done in practice is that you start with a large enough value of t. Okay, so you start with quite a large value of t, and then you keep decreasing t until the sufficient decrease criterion is satisfied. Okay, so so backtracking line search typically has the following form. So backtracking line search, that we start with t large, okay, and then while f at x minus t, so xk minus t gradient of f at xk is bigger than f at xk minus alpha t norm of gradient of f at xk squared, what you do is that you decrease t. So t, you replace t by, let's say, I don't know, a certain number smaller than 1, say 0.7 times t. Okay, or any number. I mean, 0.7 could be a 0.6 or whatever. But this is, and you know that eventually you will have to get to a value of t that will actually satisfy the sufficient criterion. Okay. So it's called backtracking because you start with a large t and you keep backtracking the value of t until you reach this condition. Okay, so yes. Okay, so let me talk briefly about projected gradient descent. So, which is what happens if you have constraints. So, constraint problem. I'll just say a few words here. So, let's say that you want to minimize a function f of x subject to x is in C, okay, where C is a convex set. Okay, so the projected gradient method as its name suggests is as follows. So you have xk plus 1 is equal to pi c of xk minus tk times the gradient of f at xk. Okay, where pi c of any variable y, this is the argmin of let me call z of let's see, so argmin of the norm of y minus z squared, so the 2 norm where z is in C. Okay, this is just the projection. This is the projection operator on the convex set C. Okay, so you have to look for the closest point for the Euclidean norm in C. So this is a very simple thing. So I mean, very simple conceptually. Sometimes it's actually hard to compute. So if this is your convex set, for example, and you have a point, this is C, and you have a point here, y, that you would like to project Okay, so the projection is exactly this point in here. Okay, so it's this point Z. Okay, this is equal to pi c of y. So some convex sets have a projection function that is easy, and other convex sets have projections that are actually hard, for which it is hard to actually for which it is hard to compute. So, for example, so for some convex sets, projection is easy. Okay, and for others, it is hard. Okay, it is just another convex optimization problem that you have to solve, which for which we do not have a closed form solution. So, for example, sets for which it is easy. So, so if C, let's say if C is just the set of X in Rn such that Xi is non-negative, okay, then projection on C is easy. Then projection on C is easy. Okay, because just the projection of psi of y on C is just a max operation. Okay, so if yi is negative, you just set it to 0 and that's it. Okay, but for other I mean, a projection on a general polyhedron, it can be difficult. So projection on a general polyhedron, so C, the set of X such that AI transpose X is less than BI, can be hard. So okay, so there are certain, so this means that the projected gradient method. So can we mute the participants? Yeah. So this projected gradient method is interesting only when the projection operation is not very costly. Okay. So this is the projected gradient method. Only when the projection operation is not very costly. And what about the convergence of the projected gradient method? Exactly, I mean, the same convergence results I mentioned before, I mean, in this lecture, do hold also for the projected gradient method. And the thing that you use a certain property of the projection operator, the fact that it's not expansive. So meaning that the norm of the projection on C of y1 minus the projection of C on y2 is less than the norm of y1 minus y2. Essentially, using this fact and related facts, you can adapt the proofs of the proofs that I've given to the projected gradient method. I will not write the proof here because later on, when we see something called the proximal gradient method, the proximal gradient method is actually a generalization of the projected gradient method, and is something that works whenever you want to minimize a function f plus a term that has a non-smooth component. In particular, it will apply to the lasso problem I mentioned this morning. And the proximal gradient method involves, as a special case, the projected gradient method. So I will talk about it more when we talk about the proximal gradient method. Okay, so okay, so I guess this is all I wanted to say. So let me just summarize. I mean, if I summarize in Word, I mean, we've looked at the gradient method. We've seen that we've seen two convergence results. One is when the function that you're trying to minimize is strongly convex. Then we get a linear convergence rate, and the rate of convergence really depends on what we call the condition number, which is L divided by mu, where L is the largest eigenvalue of the Hessian and mu is the smallest eigenvalue of the Hessian. Okay, if your function is not strongly convex, then the convergence rate is much slower. We don't have linear convergence rate. We have a sublinear convergence rate, a rate in 1/k. yes, so we've talked about the gradient method, how it is sensitive to scaling, meaning that if you scale the variables of your problem, the iterations that you get are different, and you can get a poor performance. We've seen the zigzagging behavior. This is what this picture you want to keep in mind: the zigzagging behavior for the gradient method for a quadratic function. We've also talked about if you don't have access to L and mu, then a way to choose the step size is by using backtracking line search, where you start with a large value of t and you keep decreasing t until you reach a sufficient decrease criterion. Okay, so I think this is enough for this afternoon. Tomorrow, what we will do is that we will discuss some enhancements over the gradient method. We will see how, for example, the addition of momentum allows us to speed up the convergence rate of the gradient method. And in particular, I will talk about the certain method called the fast gradient method, or the accelerated gradient method of Nesterov, which has been quite popular recently in various areas, but actually particularly in statistics and machine learning and so on. Okay, so I guess I will stop here. And okay, maybe I can look at some of the questions. Okay, let me go. Yes, okay.
Hamza?
Yes.
You have mainly 3 questions up to now.
Okay.
One related to smoothness. Why
Okay.
do you need smoothness to talk about descent methods? I think this is quite, I mean, this is a basic question.
Yes. So
what would be descent methods without smoothness? And one regarding open problems, PDE constraint optimization. What could be open problems? But maybe this question could be postponed to your late presentations. And one question regarding the comparison between conjugate versus gradient methods.
Yes, okay, so let me try to, okay, so why talk about smoothness of the function to prove it's a descent method? So, okay, I mean, we need a certain notion of smoothness to be able to analyze the algorithm. I mean, the algorithm at time step k depends just on the gradient of f. The gradient of f is something that is a local, I need to make sure that the gradient of f doesn't change very quickly as I change the value, as I change the point x, okay? I need certain regularity about the function. To be able to say something quantitative about the descent, yes, it is true that by just looking at the Taylor expansion, I know that that if I choose t small enough, it will be a descent. But I need to say something quantitative. How not just t small enough. I need to know what value of t I can choose so that to make it a descent method, and that's why I need this smoothness parameter N. For problem. Open problems, okay, PDE constraint problems, I have to say is not my specialty. So, PDE constraint problems, I guess, can show up in controls, control of PDEs and so on. If you, but this is not something I will talk about directly in this course. I will talk mostly about actually exclusively about finite dimensional problems. So yes, this is a bit outside the scope. Maybe in our Khwarizmi lecture, there is going to be something about PDEs. I don't know, Abdulrahman, can you?
Yes.
Yes, okay.
Yes, there will be lectures. The 2 coming lectures, doctoral lectures, will be related to PDE constraint optimization.
Okay.
somehow. One regarding shape optimization, which involves fundamental PDE models like elasticity, fluid mechanics, and so on. And the next one should be mean field gains, which involves, there is a link with optimization, with PDEs and optimization.
Okay.
And there are open problems in mean field gains. So Masroor will get a lot of directions on open problems.
Yes. So okay, the gamma value, I guess this is there's no gamma to choose. I mean, this gamma was just an example of a function, so it's yeah, I mean, it was just a parameter of the function. There is no we don't want to choose it or anything. It's not and then then conjugate gradient versus descent gradient. So conjugate gradient is a method to solve really a linear system of equations with a symmetric positive definite matrix. So AX is equal to B, or if you want to write it also as it's also can be seen as a least as a way to solve the least squares problem. So conjugate gradient method is actually a very good method for this problem. It has very good properties. It is typically the method to use for such problems, for symmetric, I mean, positive definite linear systems, and has much superior performance compared to the gradient method. But the conjugate gradient method doesn't apply in general for all other problems. There are versions called nonlinear conjugate gradient and so on, but that are that don't have the nice properties of conjugate gradient applied to linear systems. So yes, I mean, but yeah, that's maybe that's all I can say. And the convergence theory of nonlinear conjugate gradient is can be much harder than the one I presented here for gradient descent. So in particular, I actually do not know exactly if what is known about convergence of nonlinear conjugate gradient for minimization of a convex function. To be honest, yeah, I do not know what's known. So okay, let's see. What about for the starting point? Yes, the starting point, there is no there kind of, if you have a good guess, then just use it. If you don't have, just start from either a random point or something like this. But definitely, if you have a good starting point, then you should use it. Yes. The choice of step size, I've talked about this. If you know L and mu, then you can use a constant step size. Otherwise, you can do a backtracking line search, as I've explained at the end of the lecture. And yes, I guess these are all the questions. Yeah. Okay, people are asking about the certificate, but I think this is yeah, we talked about this already.
Well, as far as I'm concerned, I should propose to people who need a certificate to contact directly Al-Khwarizmi, the email address in Al-Khwarizmi.
Yes. Yeah.
Because neither Professor Fawzi, neither me, Habal can give you such we are not habilitated to give you such a certificate.
Yes.
Okay. Thank you very much.
Very much. And yes, so I will see you then tomorrow morning, I guess.
So next lecture will be tomorrow at 10.
Yes. Yeah. Okay.
I stopped the live streaming on YouTube. So for everybody, there will be, the videos will be available